Hello students, in this video we'll prove that self-adjoint operators on a finite dimensional vector space have an eigenvalue. Let's suppose that T maps a vector space V into V, where here V is a finite dimensional vector space. And T is linear, so linear operator. Then T has an eigenvalue. i.e., there is a vector which is not in the zero vector, and scalar lambda, which we know has to be real, such that TV is equal to lambda V. Okay, great. And so here's the idea behind this. The idea is that quadratic expressions in T, if T of course here is, well, T has an eigenvalue, and I missed one sort of a salient feature of this. So T here of course is self-adjoint. So T has to be self-adjoint for our theorem to be true, okay? So in other words, what do we know? That basically all that's saying is that T is equal to T star, or in the real case, just T transpose over here, like the transpose of the adjoint operator. So the adjoint and T are the same operator, okay? i.e., in other words, what we have is the following. This is exactly equivalent to saying that TVW is equal to VTW for every V and W in the vector space V, okay? That's all it means, right? It means that T is equal to its adjoint or its transpose. And so how do I do this over here? Well, of course, what we're going to do is the following. So let's note, here's the first preliminary observation is that if we would consider the orbit, so the proof goes as follows. Consider the orbit of a non-zero vector V. Okay. And so what does that orbit look like? So that orbit's going to look like this. And so, of course, let's make some more notation over here. Let's do this. Well, it's going to be V, and then TV, and then TV, T squared V, up to T of the dimension of V, like that. And here, let's specify the dimension of V is just equal to dimension of V is equal to n, right? And so we have over here, then we have a set of vectors, then this set of vectors over here, then the set V, the orbit T, V, T to the n, V, is a collection of n plus 1 vectors in V, and therefore it has to be linearly dependent. This collection is linearly dependent. And that's just a simple idea. All that is just saying that I have more vectors in this orbit over here, this truncated orbit, than I do in the dimension of the whole set V, right? So there's more elements in this orbit over here, this truncated orbit, than there are in a basis of V, which means that that set has to be dependent, right? In other words, there are coefficients C0 through Cn in R, such that C0 plus C1 T V plus Cn Tn V is equal to 0. And these coefficients are not all 0, right? Not all 0, right? And of course, the idea now is to factor this polynomial expression in T, right? So that's a polynomial expression in T, which can be factored, right? So I can factor this into a whole bunch of quadratic factors, right? So by the fundamental theorem of algebra, we can factor this, right? So we're going to have a whole bunch of what? We're going to have a whole bunch of T minus lambda 1 identity. You have some real roots over here, T minus lambda L identity. And you'll have some quadratic expressions over here that are not reducible over R, right? So T squared minus, let's say, alpha 1 t plus alpha 1 t plus beta 1, and then t squared plus alpha, let's say k, alpha kt plus beta k, applied to v is equal to 0, where of course these quadratics are irreducible, right? So b squared minus 4ac is less than 0. So that says that alpha I squared minus 4 beta I is less than what? That is the discriminant of these things. That has to be less than 0, so we get complex roots that are irreducible over there. That's the criterion that we have over here. That's equivalent to saying that alpha I squared is less than 4 beta I squared here. And this is true for I between 1 and k. 1 less than or equal to I, less than or equal to k over here, right? And of course, the restriction over here is that we have L, which is the number of linear terms, and then plus 2k over here has to be equal to n, the dimension of this, or excuse me, has to be equal to the dimension of the n, the degree of the polynomial over here, right? So in other words, 2k, those are the number of the degree of the quadratic terms, and then plus L has to be equal to n, right? So whatever that happens to be, right? Now, I want to show that none of these quadratic terms can actually give me a 0 in my vector v. In other words, I claim that these factors over here are actually invertible since t is self-adjoint. So let's prove that. So our claim, so suppose, here's a proposition or a lemma. If alpha squared is less than 4 beta, like in this condition over here, then t squared plus alpha t plus beta identity is invertible. Okay, so proof of that is straightforward, right? So proof, if v is not equal to 0, then consider t squared plus alpha t plus beta applied to v with v, this inner product over here. And then what will I get? Well, this t squared vv is going to be exactly just tv tv. By the fact that t is self-adjoint, I take one of the t's in the squared and throw it on the other side, plus alpha tv tv. And then what? And then plus beta vv. Okay? Now, of course, this is just the norm of tv squared over here, right? That's just beta, the norm of v squared. Just beta. There's no beta squared, just beta, right? Okay, beta, norm of v squared. And then these other terms over here, these alpha and then tv with v, like that. Now, I want to make this bigger than or equal to something to show it's non-zero, right? This is bigger than or equal to by Cauchy-Schwarz, tv square. I'm going to suppress the vector notation. And then minus alpha norm of tv, norm of v. And then what? And then plus what? Plus beta v squared, like that, okay? And now what can I say about this thing over here? This is a quadratic expression over here. Now what can we say? We can say this is a quadratic expression in the expressions tv and v over here. And so since what we can do is now we know that alpha squared minus 4 beta squared, so the discriminant of this expression is a function of as a expression that involves tv, right? So in other words, this is a quadratic expression in tv. I can show that this expression is always strictly greater than or equal to 0 since what? Since alpha squared minus 4 beta is less than 0, right? So I can complete the square over here and show that this is always greater than or equal to 0. So there's a quadratic form in TV that's greater than 0, but due to this restriction on alpha squared minus 4 beta squared. So all of these terms over here, that proves our lemma, right, by the fact that this is positive definite over here. And so all of these terms are invertible. So if I can commute these things, and all of these things, because they're all just expressions of t, so any one of these quadratic terms applied to v will not get me 0 since they're invertible. So in other words, if I plug in a non-zero vector into v, a non-zero vector into an invertible matrix, or invertible operator, I will not get the 0 vector out, which means that one of these things has to fail to be injective, right? So in other words, there exists a j that's between 1 up to L over here, such that T minus lambda J identity V is equal to 0, and then that over there shows that this matrix over here is not injective over here, but in finite dimensional spaces, being not injective is equivalent to being not invertible, so this is not invertible, and then this lambda J over here and this vector V gives me my eigenvalue of lambda J and my eigenvector of V, which proves that a self-adjoint operator on a finite dimensional vector space always has an eigenvalue, and this is the base step in the induction of the spectral theorem for self-adjoint operators over a real vector space. Thank you very much.